Hello everyone, welcome to our YouTube channel Calculus Hub UPI Cairo. This is video number 6 in Calculus 2 course. Title of this video is Applications on Definite Integrals. This title is covering three topics. Now we are going to start with the first one, which is volume of rotating area, disk method and the washer method. I'm Hisham Hosni Hussein, Associate Professor of Applied Mathematics. Please prepare your pen, your notes, and let's go. Assuming a curve y equals to f of x, curve in the xy plane, okay, and this curve is rotating about any of the axes, rotating about x-axis, y-axis, or even it's rotating about horizontal or vertical axes, like this one. Here, this y equals to f of x in general, and this curve after rotating it about x-axis, this is the resulting shape after rotation about x-axis. Here we take like a cross section of this shape. This cross section in the form of compact disc. This is the form of the cross section. This is the form of the compact disc. Here we have thickness, which is corresponding to the height of this sphere. This thickness is parallel to x, so it's dx, and the radius of this cross section is corresponding to radius of this cylinder. Here the radius is parallel to y-axis, so it will be y. So now to find the volume of this element, cross-sectional element, so it's an element of volume dV equals to, we know that the volume by r squared times h, so the volume of this element is by, the radius here is y, it's y squared times the thickness here is dx. So to find the volume of the whole shape, integrating both sides, integration of dv equals 2 by is considered as a constant, integration of y squared dx. Integrating both sides, then the volume of whole of the shape will be by integration of y to the power 2 dx, where this y is a function of x. Here is the rotation about x-axis, volume which is resulting from the rotation about x-axis. What if we would like to find the volume of rotating curve about y-axis? So this equals to by integration of x squared, but here it's dy, where this x is a function of y. But what if you would like to rotate an area about any of the axes, and this x is different from x or y axis? Like this axis, which is y equals to, for example, b. Assuming that here we have a curve, assuming that here we have a curve y equals to f of x, and we would like to rotate this curve about y equals to b. So this is the radius of rotation. Here this x axis, this y axis, and all of this distance is y. However, this is the radius of rotation. We can recall it as r. So now this radius r equals to y, which is f of x, minus this b. So to find the volume of rotation about y equals to b, this equals to by integration for our radius f of x minus b squared dx. What if we would like to rotate about a vertical axis, like x equals to a? We need to rotate this area about x equals to a. Equation of this curve is x equals to g of y. Here this x equals to a, which means that the radius is all of this a minus x equals to g of y. So the radius of rotation here is a minus g of y. So the volume which is resulting from rotation about x equals to a equals to by integration a minus g of y squared dy. Here in problem 1, find the volume of the solid that resulting when the shaded region is revolved about the indicated axis. In this area, we need to rotate about x-axis. This area, we need to rotate about y-axis. So for this one, volume which is resulting from rotation about x-axis equals to by integration. Here, y equals to root 3 minus x. It's root 3 minus x square dx. X here is running from the start of x and the end of x. This is the start of the limit and the end of the limit. X here is starting from -1 to 3. That's it. Just square the integrand v resulting from rotation about x. This equals to by integration from -1 to 3. This 3 minus x dx. Now this just integration problem. It's by integration of 3. This 3x. Integration of x. This half x squared running from -1 to 3. Substitute with the upper minus substitute with the lower. This equals to by substitute with the upper. Here it's 9 minus 9 over 2 minus substitute with the lower. It's -3 minus half. This value is the requested volume. Here in problem 2, it's requested to rotate this shaded region about y-axis. So the volume here, volume which is resulting from rotation about y-axis, this equals to by integration of x squared dy. What is x? This root 1 plus y. It's root 1 plus y squared dy. Y here is running from -1 to 3. So it's by integration from -1 to 3. Apply the square. It's 1 plus y dy. Integration of 1, it's y plus the integration of y, this half y squared. Integration from -1, integration from -1 to 3. Just substitute with the upper minus substitute with the lower. This equals to pi, substitute with the upper limit, it's 3 plus 9 over 2. Minus substitute with the lower, this -1 plus half. This value is the volume of the rotating shape. Here in problem 5, it's requested to find the volume which is resulting from rotating the region R about y equals to 1. So it's requested first to find the radius of rotation. So the radius of rotation will be 1 minus root x, which is root x at the end. So the volume which is resulting from rotation the region R about y equals to 1 will be by integration for the radius which is root x power 2 dx. X is running from the first value. This is the first value for the region x-axis. Here x equal to 0. Here x equals to 1. So the integration is running from 0 to 1. This equals to pi integration from 0 to 1 root x power 2 this x dx is by integration of x, this x squared divided 2 from 0 to 1. Substitute with the upper minus substitute with the lower. It will be pi over 2. In problem 6, to find the solid which is resulting from rotating the region R about the line x equals to 2. So we need first to find the radius. The radius here is the difference between these two values. Here x equals to 2 and x equals to 2 minus sec y. So the radius is 2 minus sec y, which is sec y. Then the volume which is resulting from rotating from the rotation about x equals to 2 is by integration from y equal to 0 to y equals to pi over 3. The radius power 2, which is sec power 2y dy. What's the integration of sec squared? This 10. So this equals to the volume from rotation about x equals to 2 is pi times tan y. The limits from 0 to pi over 3. Substitute with the upper minus substitute with the lower. It will be pi times tan pi over 3. Minus tan 0 for sure, which is 0. So this is the resulting volume. For this problem, y equals to 1 minus x squared. It's requested to find the volume of rotating this area about x-axis. So start first by sketching y equal x squared. You have to sketch in this type of problems. If the sketch was not provided, so you have to sketch it. Okay, so y equals to 1 minus x squared. 1 minus x squared. This is the same as this one. So it's requested to rotate this region about x-axis. We need to find the intersections between y equals to 1 minus x squared and x-axis. We have y equals to 1 minus x squared and y equal to 0. So we get that in 1 minus x squared equal to 0. So x equals to plus or minus 1. So here x equals to negative 1 and here x equals to 1. So the volume of rotating this area about x-axis, this equals to by integration. Equation of this curve is 1 minus, function of this curve is 1 minus x squared. So it's integration of 1 minus x squared power 2 dx. The integration here is running from negative 1 and 1. We know that in this even function, and integration is running from negative 1 to 1. So it's 2 by integration from 0 to 1, 1 minus x squared power 2 dx. Expand, this will be 2 pi, integration from 0 to 1. First square is 1, first times second times 2 minus 2x squared. Second square is x to the power 4 dx. For each function, raise the power by 1 and divide by the new power. It's 2 pi, integration of 1 is x minus 2 over 3 x power 3 plus 1 over 5 x to the power 5 with the limits from 0 to 1 equals to 2 pi times 1 minus 2 over 3 plus 1 over 5. The disk method that we discussed recently is working if the axis of rotation is one of the borders of the rotating area like this one. Here, assuming that we are rotating this area about the x-axis. Okay, so here we use the disk method. But what if we have an area like this one, and there is a space between the area, the rotating area, and the axis of rotation like this one. Here we have space like this. This is space. So in this case, we use the washer method. Here we have two radii. Here we have two radii. This is the outer one, and here this is the inner one. The point here is we subtracting, assuming that in here this is the boundary for the region. So here we subtract the rotating boundary. So here we subtract the whole volume, the volume of the space. So here we subtract the volume of the hollow between. So here we have two volumes. We subtract the volume of the hollow from the total volume to get the requested volume. So the volume of rotation about x-axis here equals to total volume minus volume of the hollow. Okay, volume of the hollow here has inner radius r small. The total volume has outer radius r capital. So volume of rotation about x will be by integration r square dx minus pi integration r square dx. Or in other form, we can write it as volume of rotation about x equals to by integration r square, r capital square, or r outer square minus r inner square dx. And we can do the same. Here this is the rotation about x-axis. The rotation about y-axis will be by integration r but here it's r of y, here it's r of x, here it's r of y, r outer minus r inner square of y dy. And we'll do the same if we are rotating about any of the axes different from x or y axes. Okay, here for this set of problems, find the volume of rotating this region, this shaded region, about x-axis. As here we have a space, here we have a space between the shaded region, the area of rotation, and the axis of rotation. So this means that we are going here to use the washer method. The washer method. Okay, to solve using washer method, we need two radii, the outer one and the inner one. Here is the outer radii and here is the inner radii. So this means that we need two radii. It's the outer radius and here is the inner radius. So the outer radius will be this is the curve, this is the blue curve, which is y equals to 2 minus x squared. This 2 minus x squared. The inner radius or the smaller radius is y equals to x. This or small, this y equals to x. So the volume of rotation about x-axis, this equals to by integration. The outer radius squared is 2 minus x squared power 2 minus the inner radius, which is x squared dx. X here is running from this x, y-axis, which is x equal to 0 to this point. Okay, so how to find the x coordinate of this point? Simply 2 minus x squared equals to x, or in other form, x squared plus x minus 2. This equal to 0, which is x plus 2 times x minus 1. This equal to 0. This gives two values, x equals to negative 2 and x equals to 1. So the integral here is running from 0 to 1. So the volume is pi integration from 0 to 1, first square, first times second times 2, second square, minus x squared dx. Simplify the integrand. It's pi integration from 0 to 1. It's 4 minus 5x squared plus x power 4 dx. Integrate. This pi. What's the integral of 4? It's 4x minus 5 over 3x power 3 plus 1 over 5x power 5 with the limits from 0 to 1. Substitute the limits. This would be pi 4 minus 5 over 3 plus 1 over 5. This value is the volume of the rotating area. For this problem, for the second problem, it's requested to rotate this area about y-axis. So here we have two radii. This is the outer radii, or this is the large radii. So here we have two radii. This is the big radius, and this is the smaller radius. Okay, so for the big radius, or capital, x here is 2. This distance is 2. Regarding the smaller radius, here the equation of this curve is y equals to 1 over x, as clarified. So y equals to 1 over x, but here we are going to find the volume of rotation about y-axis. So we need to represent each function as a function of y. So x equals here 1 over y, which means that in here we have the smaller radius 1 over y. So the volume of rotation about y-axis equals to by integration the larger radius, which is 2 power 2, this 4 minus the smaller one, r equals to 1 over y power 2, which is 1 over y squared dy. Y is running from this point to this one. Clearly, the maximum one, it's clear that in the maximum y is 2. The smaller y is the intersection between x equals to 2 and x equals to 1 over y. So the intersection between x equals to 2 and x equals to 1 over y So 2 equals to 1 over y, which means that in y equals to 1 over 2. So the volume of rotation about y-axis Vy is y, integration with respect to y, this 4y. Here we can replace this 1 over y square by y to the power negative 2. Its integral will be y to the power negative 1 divided negative 1. The limits from half to 2. Half to 2. So Vy is by, substitute with the upper, this, 2 times 4, this 8, minus this plus 1 over 2. Substitute with the upper, minus substitute with the lower, this 2 plus 2. This is the volume of the rotating area. In this problem, find the volume that's resulting by rotating two curves. The first curve is in y equals to 1 over 4x square and y equals to 5 minus x square, rotating this area about x-axis. So start by sketching y equals to 1 over 4x squared is the same as this curve, and y equals to 5 minus x square is the same as this one. It's negative x square sketched 5 steps up. Okay, so the target is find the volume by rotating this area about x-axis. Okay, so here we have two radii. This is the first radius. Here we are going to rotate. It's about x-axis. Here this is the larger radius. This is the smaller one. The larger radius, the curve y equals to 5 minus x square. 5 minus x squared. The smaller one is y equals to 1 over 4x squared. This is the smaller one. Y is 1 over 4x squared, which is the same as x squared divided 4. Okay, so the volume from rotating this area about x-axis, finding this volume using the washer method. Why using washer method? As in here we have a gap between the area and the axis of rotation. If you don't have a gap, so use the disk method. So the volume for rotating this area about x-axis is by integration of the upper radius square minus the lower one square dx. This equals to by integrate the upper radius square or the largest radius square 5 minus x square power 2 minus the smaller radius square, which is x squared divided 4 power 2 dx. What about the limits? Equate both curves. X squared divided 4 equals to 5 minus x squared. 5 minus x squared. This means that in 5 over 4x squared equals to 5, or in other form, x squared equals to 2. By solving this equation, x equals to plus or minus 2. So the integration here from negative 2 to 2. This equals to 2 by integration from 0 to 2. Expand first square 25 first times second times 2 minus 10x squared, the second square plus x power 4 minus 1 over 4 squared, this 1 over 16 x to the power 4 dx. Collect the like terms. This equals to 2 by integration from 0 to 2. 25 constant as it is minus 10x power 2 x power 4 minus 1 over, minus 1 over 16 x power 4, this 15 over 16 x to the power 4 dx. Integrate this 2 pi integration of 25, this 25x minus 10 over 3 x power 3 plus 15 divided 16 x to the power 5 divided 5 with the limits from 0 to 2. Simplify and now substitute with the limits. Substitution with 0 will lead to substitution with 0. You will get 0. Substitution with 2, you will get 50 minus 80 divided 3 plus 32 times 3, this is 96 divided 16. This is the value of the resulting volume. Find the volume that's resulting from rotating the area y equals to x squared and x equals to y squared about the line y equals to 1. Here this y equals to x squared, x equals to y squared. About the line y equals to 1, here this y equals to 1 starting from needs the line y equals to 1. It's a line passing through the intersection point between the two curves. Y equals to x squared and x equals to y squared. X equals to y squared. This leading to y equals to root x. We are working in the positive quad. Here this y equals to root x. Here this y equals to root x. Rotating about the line y equals to 1. As in we have here a gap. So using the washer method. Washer method. Okay. So we need to determine. So we need to find out where is the. So we need to find out where is the large radius and where is the small radius. This is the large radius and this is the small one. Equation of this line is y equals to 1. So the large radius, our capital, is 1 minus x squared. The smaller one is 1 minus root x. So the volume that's resulting from the rotating this area about y equals to 1 is by integration of this area from 0 to 1, starting here from the origin till x equals to 1. Okay, the large radius is 1 minus x squared power 2 minus the smaller one, which is 1 minus root x squared dx. So evaluate this integral. The volume resulting from y equals to 1 equals to by integrate from 0 to 1. The first square, which is 1, the first times second times 2, minus 2x squared. The second square is x to the power 4. Minus the same expand this bracket here, this 1 minus 2 root x, 2x power half plus the second square plus x dx. Simplify. Here we have 1 minus 1. The resulting integral will be by integration from 0 to 1, negative 2x squared plus x power 4, negative this positive, 2x power half, negative x dx. Now integrate. This equals to by, evaluate the integral, negative 2 as it is, x power 3 divided 3 plus x to the power 5 divided 5 plus 2 x to the power 3 over 2 divided 3 over 2 minus x. Its integral is x squared divided 2 with the limits from 0 to 1. Substitute with the upper minus substitute with the lower. You will get by times negative 2 over 3 plus 1 over 5 plus 4 over 3 minus half. Find the volume resulting from rotating the area. The description of the area is y equals to ln x and x equal to 0. With the boundaries, y is running from 0 to 1. The rotation, the axis of rotation is x equals to negative 1. So start by sketching y equals to ln x. Y equals to ln x. This one. And x equal to 0, this y axis for sure. X equal to 0 is y axis. Y is running from 0 to 1, the boundary, y equals to 1. Here, this y equal to 0. This is the requested area to rotate. Y equals to 1, y is 0, y is ln x, and x equal to 0. Okay, the axis of rotation, the axis where the area will rotate about, is x equals to negative 1. X is negative 1. Okay, so here we have two radii. This is the large radius. This is the small one. This is the large radius, R capital. This the small one, R small. Okay, so to find the large radius from x to x, from x to another x, here we are measuring horizontal distance. Y equals to ln x is corresponding to x equals to e to the power y. Here, this x equals to negative 1. So the large radius is r equals to e to the power y minus negative 1, which is e to the power y plus 1. This is the large radius. The small one is the distance, the horizontal distance from x equal to 0 to x equals to negative 1. 0 minus negative 1, which is 1. Now integrate. So the volume here for sure we have a gap between the area and the axis of rotation. Here is the gap, which means that we are going to use the washer method. So the volume resulting from rotating the area about the axis x equals to -1 equals to by integrate the large radius square, which is e to the power y plus 1 square minus the smaller radius square, which is 1 to the power 1, which is 1 to the which is 1 to the power 2 dy. Y is running from 0 to 1. This equals to by integration from 0 to 1, expand this perfect square, the first square e to the power 2y, first times second times 2 plus 2e to the power y plus the second square minus 1 dy. Cancel 1 and 1. This equals to by e to the power y, its integral is e to the power 2y divided 2 plus 2 e to the power y as it is, with the limits from 0 to 1. Substitute with the upper minus substitute with the lower. It's pi times substitute with 1. You will get half e to the power 2 plus 2 e to the power 1 minus substitute with the lower, substitute with 0. You will get half plus 2. Just compute on the calculator to find the volume resulting from rotating this area about the line x equals to -1.